Okay, so I'd like to thank the organizers for this invitation and you all for coming. Here you have the pictures of previous and current postdocs and students who have been involved in the things that I'll be talking about. Okay, so I'm going to start with a long introduction. It's a long review of some of our works about the dynamical manifestations of many-body quantum chaos. Also, a brief review about the problem of self-averaging, and only by the end of the talk, I'll tell you what we are doing now. Okay? So the term quantum chaos here, I'll be using it as a synonym of spectral correlations as in full random matrices, which you could quantify, which you could detect by studying level spacing distribution, or if you want a more complete analysis of your spectrum, taking into account also long-range correlations, you could look at level number variance or rigidity, or you could look at the spectral form factor, right? So the spectral form factor is the Fourier transform of the two-point spectral correlation. When you have these full random matrices, when we have chaotic systems, then the spectral form factor exhibits this structure where you see a dip, a ramp, and then this plateau. And there are some advantages in using the spectral form factor when we are doing level statistics. No? For example, as I already said, you can detect short and long range correlations. You don't need to do unfolding. You will see that structure if your system is chaotic. And you don't even need to take account of the symmetries. You don't need to separate the levels by symmetry sector. So here I'm showing an example of this issue. No? We have two models, spin half model and spin one model. They are chaotic, but they are symmetries. We didn't take the symmetries into account, and you have there a Poisson distribution. But if you look at the spectral form factor, you will see that structure there. And so it has its advantages. Now, this structure, this dip, ramp, plateau, I'll be calling it the correlation hole. And why correlation hole? Because this term was introduced back in the 80s, especially in the context of molecules. So it's a nice thing. It started there in discussions in chemistry, because the issue in chemistry is that when you have the spectrum, you don't have such good resolutions as when you have nuclei. The levels can overlap. So the idea is, well, to detect these correlations, better to do Fourier transform. Go on. But few, but enough to hide it. No, you got a Poisson. Right. Okay, and then, okay, so coming back to the correlation hole, so these guys decided to do the Fourier transform. No? And then, if the levels are correlated, you'll get that structure, so natural to call it correlation hole. No? And the term was used in many other works back in the 80s, 90s, and later. If you look at these papers, there are papers by quantum chaos people, by chemists, and so on. Some of these works were discussing not only the spectral form factor, but also the survival probability or return probability. And that's the quantity that we've been studying. So the probability for detecting the initial state later in time. So if we project this state in the energy eigenbasis, we get these phases here, just as in the spectral form factor. But in addition to that, we have the components of the initial state. So we are not putting a filter here. We really want to study a physical initial state, something that an experimentalist can prepare. And so we have this physical, this experimental initial state. We are going to let it evolve according to a physical model. And then we want to tell the guys, well, you're going to see the correlation hole at this time scale. Okay? All right, so we started studying the survival probability with Jonathan back in 2016, 17, but in the context of many-body localization. So what we are doing there at the time was, well, this is an extra tool to study the transition. So as we increase disorder strength and we move away from chaos towards a possible localized phase, what happens to the hole? It gets postponed to later times, and it shrinks, and eventually disappears because we kill the correlations. At that time, with Jonathan, we were trying to identify some other quantity that would also exhibit this structure. that would also exhibit the correlation hole. We had looked at some like entropies or like a participation ratio, but a dynamical version of the participation ratio, and we wouldn't see anything. We sometimes would see a tiny hole, but was negligible. No? And then Jonathan finally came up with the idea of at looking at the spin autocorrelation function. And there you see also the correlation hole. No? So the spin autocorrelation function is this one. Many people talked about it in these talks this week. The advantage is a local quantity, can be measured in NMR, is equivalent to the dense imbalance measured in cold atoms. Now think about now state up, down, you have the imbalance here. So we were happy about this. It's showing at long times, but we were happy about that. What we are trying to do, and it's already in this paper, we are trying to get some analytical result. We could see that the time for the hole was super long. But we are trying to get some analytical results so we could have an analytical expression for that time. There is an expression already in that paper, but we did things in much more details with Mauro. Where we obtain an analytical expression for the whole evolution of the survival probability. With an analytical expression, we can get analytical equations for those time scales. And the time for this beginning of the ramp is proportional to d. D here is the dimension of the Hilbert space to this power 2/3. So this is a point of concern here, right? This is extremely questionable. I'm going to show to you later when I go through details, but this is any kind of many-body quantum system with two-body couplings. We were looking at short range. We were looking at spin halves, but if the system is chaotic, oh no, we also have results for spin 1. If the system is chaotic, it will show up also in spin 1 or any other, both Hubbard as well. It should be, let me get to that point and then we come back if I don't remember, okay? It all depends on the initial state, on the strength of the perturbation, things like this, but you can get a general picture. I come back to this, okay? So, grows exponentially with the system size, so it will take forever for this system to finally thermalize, or for this quantity to finally thermalize. So, if we want to see this experimentally, we have a problem, right? It's long times, tiny values, and on top of that, we have another problem, which is these quantities that exhibit the correlation hole, they are non-self-averaging. What does that mean? If you pick just one realization, one disorder realization, one initial state, you have these enormous fluctuations there. And so you cannot see a hole there. So you need to do these averages. So it's one extra problem in the detection of the correlation hole. So this is the discussion so far. What we are doing now is, okay, how can we circumvent these problems for the experimental groups? No? To detect the correlation hole, we said, well, let's do the most obvious thing. Let me shrink this system. Let's see how small I can go, how far I can go in tiny size, and still see the hole. Okay? The problem of lack of self-averaging, then this is something that we've been doing with Adolfo Del Campo, is to reduce those fluctuations, open the system to the environment. Okay, so these are the two works that I'll come back at the end of the talk. So then now I start with this long review, as I told you. Okay, so first let's look at the evolution of the survival probability, but under full random matrix from a GOE ensemble. So let me assume that my initial state comes from this diagonal part of the matrix. So this is the unperturbed part, and I'm going to evolve it according to this whole thing. So if you want to do that, it's very simple. You diagonalize the matrix. These are your vectors, random vectors. You pick a line here, and that's your initial state. So completely unphysical. Why do we do that? Because we can get analytical results. Random matrices, correlated eigenvalues. This is the expression that describes the whole evolution under random matrices, and we are showing here with this red line, and black is the numerics. So what do we have in this equation? This bar here is indicating the saturation, the plateau, 3 over the dimension. This is result from GOE, random numbers. This B2 is the two-level form factor, is describing the correlation hole. And what do we see before is described by this part here. This is a Bessel function of first kind. Where does this come from? We could also write the survival probability like this. What am I doing? So this is the sum. These are the components of the initial state. I can write this sum with an integral. So what do we have here? The absolute square of the Fourier transform of this rho. This rho is the energy distribution of the initial state. So, and what is the energy distribution for random matrix? This semicircle. Fourier transform of that is that Bessel function. So this describes the initial behavior. What do we have? These oscillations from the Bessel and this power law decay with exponent 3. The exponent 3 comes from the bounds in this spectrum. All right. This is our analytical result, but now let's have a look at the dynamics for different sizes of this dimension. What do we see as we increase? Well, of course, the survival probability gets very small values, but the point where we start the whole is always the same. It's a constant, and it came from that equation. So where we detect the spectral correlations, that's a constant, but to reach finally saturation, that is a time that grows with the dimension of the Hilbert space. This is Heisenberg time, inverse of the mean level space. Okay? So for this quantity to finally equilibrate, we have to go all the way to Heisenberg. So here, what we are, it's very artificial. No? So what I picked, this is my initial state. So I have a random matrix. So these are my eigenvectors. And I picked a line. And I said, this is my eigenvector, well, my initial state. When you're dealing with random matrices, you just have a whole bunch of random vectors. And so things do not depend much on what you pick. Random matrices, these components are all random numbers. These levels are all correlated. So things are much easier. All right, so now come to which system. So I'm going to illustrate that for the famous model used, oops, I pressed the wrong button. The model used to study many-body localization. So this is the model that has been used to study many-body localizations since 2004 at least. So the initial state is an eigenstate of this part. This is the unperturbed part, the on-site disorder, and the easing. So this is the kind of initial state that we could prepare with cold atoms, with ion traps. It's an experimental initial state. And we let it evolve according to that whole Hamiltonian. Let's start looking at the chaotic regime. So small disorder strength, chaotic regime. And I'm going to pick initial states in the middle of the spectrum where I know chaos can develop. And what do we see? So following the same steps for here, since I'm in the middle of the spectrum, let's see if I have an equation for, since I'm in the middle of the spectrum, these components, even in the physical model, is very similar to random numbers. I have correlations. No? These two things, the eigenstates and the level statistics are, the eigenvalues are statistically independent. Okay? So what is it that we are going to get? An equation that is similar to that. The saturation, which is also 3 over the dimension, the B2 that is going to describe the correlation whole. What changes? The initial behavior. And where is this initial behavior coming from? The energy distribution of the initial state, which is no longer a semicircle, it's a Gaussian. The density of states of any many-body system is Gaussian, with short range, not all-to-all coupling, but so any distribution, the density of state is Gaussian in these many-body systems, few body couplings. Because I picked an initial state in the middle of the spectrum, strong perturbation, I'm going to have this Gaussian shape as well. So this is general. Of course, you can look at other possibilities. If you start going closer to the edge of the spectrum, so then you don't have this nice Gaussian, you have a skewed Gaussian. If you have the perturbation is not too strong, instead of a Gaussian, you could have a Lorentzian. Or you could play with other initial states. I'm just looking at this general picture. Okay, so Fourier transform, the Gaussian gives us the Gaussian decay. The bounds here gives us a power law with exponent 2 now, not 3, but 2, because of the Gaussian. And what happens to the time scale now is that story that I was telling you in the beginning. The time for the beginning of the ramp grows now, grows with the dimension of the Hilbert space to that power. There is a conservation, right, in this case, so but it's exponentially large in L. It's L, in half filling, so L factorial, L over 2 factorial squared. Yeah, so remove the D and put the 2 to L. Okay? It's not 2 to L because I'm in a symmetry sector, but it's approximately. Yeah? So it's exponentially large in L. Just as the Heisenberg time, you know it's exponentially large in system size. It's the same thing here, but to this power 2/3. Where did this come from? From that analytical expression. This guy is taking us down. This one is bringing us up. Where they meet is this expression. And the Heisenberg time also came from that expression, where this function finally meets the ramp. Okay? So grows exponentially, yeah. The power law here. So when you do the Fourier transform of this Gaussian, you don't do a Fourier transform of a Gaussian that has no limits. You do with the bounds, so you get an error function. And if you look at this error function long times, that gives you this power law behavior. Yeah, it's because of the spectrum is bounded, we are studying finite systems. Yeah, because we are studying these finite systems. And so that's the issue that I said, well, big deal, it will take forever to thermalize. And the same story for the spin autocorrelation function. The whole shows up at the same time scale. The initial behavior may be different, but once we reach this time, this point, is when the dynamics resolve the discreteness of the spectrum. We are detecting correlations among these eigenvalues. So it doesn't matter if I'm playing with survival probability or spin autocorrelation, the result is the same. Okay, good. So this is chaotic regime. We have these analytical expressions for the survival probability. Now, what happens as we increase disorder strength? So there are different features now to discuss. So first thing, if I look at that intermediate time, the story of the power law behavior, what is going to happen? As I increase the disorder, that exponent will get smaller and smaller. And you see that I separated red region from green region, and let's try to understand what is the difference here. Okay? This is the region where we have chaos. Okay? So what is the source of this power law behavior is what we are talking about, the bounds in the spectrum. So in this chaotic regime, this energy distribution is ergodically filled. And so we detect the bounds. Is that Fourier transform that I was talking about with these bounds. That gives us these 2. In the case of random matrix, it gave us 3. Now, if I keep increasing the disorder strength, we reach this region here. As we keep increasing the disorder strength, now these things are no longer random numbers. No, they become correlated. Where I cannot separate eigenstates from eigenvalues anymore. So this correlation is the source of this power law behavior. So this is similar to what Leo was telling us on Monday. Remember, in non-interacting systems, people try to connect this exponent with the fractal dimension. We try to do this also in this interacting model with Jonathan, but I think there is improvement in this direction. Okay, but the fact is there is a power law behavior, and where should it be coming from? From this correlation. So 2 different sources. We could never try to connect this with fractal dimension because this is exponent 2. It's only when the exponent becomes smaller than 1 that we could do that. Fine. But what comes next? What comes later in time is the region of spectral correlations. So there we have the correlation hole. As the disorder increases, getting postponed to later and later times, getting shrinking until it disappears. Fine. So this we had already discussed in these papers. But what we did with Mauro, and this paper is long, there are many details, was to study how this time, the time for the beginning of the ramp, how does it depend on the disorder strength? And then what we see is that it grows exponentially with the disorder strength. So what we are discussing in that paper is, well, if there would be a localized phase, that would be when the tau is, or the time of when the ramp starts, would hit the Heisenberg time, when this ratio would go to 1. And then later, you probably know Leo's paper, they show the same thing, this growth with the disorder strength. What else did we do in Mauro's paper was, well, in addition to the ramp for the survival probability, we studied it for the spin autocorrelation function. And again, the same behavior growing exponentially with the disorder strength. All right, so it looks like there is a strong parallel between these two quantities. And there was the talk yesterday talking about this connection between spin autocorrelation function and survival probability. But there was something that we were suspecting already when we started going to larger system sizes, larger than 16, which we formalized in a later paper with Talia, which is the following. So there is a difference between survival probability and spin autocorrelation function. Here we have the correlation hole for random matrices. In the analysis of survival probability, the hole is always there. The minimum of the hole is 2 over the dimension. The saturation point is 3 over the dimension. This is all analytical results for GOE. So we introduce this relative depth, which is the saturation minus the minimum, so this difference here, divided by the saturation. Well, this relative depth is 1/3 for random matrices. It doesn't matter how big the matrix is. So the hole survives. When we go to physical models, again, this dashed line is that 1/3 from random matrices. When the system is small, well, you're not really there, but you increase the system size and you really reach that point. So it's robust. What happens now with the spin autocorrelation function? So if you play with small system sizes, well, it looked like the thing was there, the hole was there. But as we increase much more, we start seeing that above 16, that this was decreasing. So it is indicating that the correlation hole will disappear for the spin autocorrelation function. How about other quantities? This is the inverse participation ratio, a dynamical kind of inverse participation ratio, and that is measuring how this initial state is spreading into other many-body states. If you look at this plot, you don't see any correlation hole. You wouldn't know that it exists. To see it, you could see, if you really zoom in, so this is multiplied by the dimension, you see this tiny thing over there. But it's tiny, and that relative depth decreases as you increase the system size and decreases exponentially in this case. So all that motivated us to try to then introduce a new relaxation time for the quantities that do not exhibit the correlation hole or have this tiny correlation hole. And this time was the point where we would first cross the saturation. This time, so it's marked with these crosses here. So this time still grows with system size, but at least it's polynomially. I think there is much more to be done here to polish these results, look larger system size, dependence on disorder strength, and so on. Okay? But the message is thermalization depends on the model, depends on the initial state, and depends on the quantity as well. All right. That's the big review. Now I'm going to start telling you a little bit about what we are doing now. And this should be quick. I thought there would be more questions. But, so, as we said, tell me. I asked for a question.
So, what is the relation of if I do the ramp at a given temperature and what you do? But imagine that I choose the state you use with that temperature, with a Gibbs measure of that temperature. Is the return, the one calculated from the return time with a state chosen with a Gibbs measure with beta, the same as doing the trace with e to the power minus beta
No, I didn't understand. So you want to know what is the time scale if I use some thermal kind of initial state?
Exactly.
And if this temperature is infinite or not. So it's basically playing with different kinds of initial states, right? So it could be much slower if you're very, very low temperature. The beginning should maybe.
But my question is more, if I do a thermal average and on one side, and on the other side I choose only one state, but from that appropriate energy of that temperature, do I get similar results?
What are the two sides?
One is a single state chosen with a Gibbs measure, but only one. And the other
without averages.
Without averaging. And the other one would be doing the thermal trace.
And then, okay, if there are no averages, you risk not seeing the whole. But you want to know whether, I don't understand very well, whether if I do a thermal average or not, if these results should...
It change.
If you are able to see the whole, even without seeing even without doing the average, I would say that they should both show up at the same time because you're reaching the just spectral correlation, so that should be at the same time scale. Okay, so what we started doing with Edway and some help from Patrick was, okay, let's look at the tiniest chain that we can play with. So we play with Heisenberg model, thinking about cold atoms, the long-range Ising model, thinking about ion traps, survival probability, spin autocorrelation function, because if the system is small, we should see the whole there as well. And just summarizing this story, even for just 6 sites, we do see it. When we are in the chaotic region, if we go large disorder, the whole disappears. So with Edway, what we are trying to do is, let's try to mimic what an experimental group would do. So how would they measure the survival probability? Well, they let the system evolve at a certain time t, collapse the wave function, and then do this again and this again. So you do like m shots, and out of these m shots, so it has to be many, out of these m shots, m1 times you get to the initial state. So this ratio would be the value of the survival probability. So you need a big number of shots, and then on top of that, the initial states, and on top of that, the disorder realization. So we try to do this big repetition, but to a number that was not bigger than 10 to 4, something that could be reasonable for an experimental group. And what is the purpose of that? We would look at the distributions, and we want to be sure that the distribution for the minimum of the whole and the distribution and the saturation are well separated, no overlaps. So that's what we see, while once we are here, there are overlaps. And if we pick some times on the ramp, the average, the mean value here should increase monotonically, while here they oscillate. So the message is, maybe, guys, it's not that bad. Maybe you could see it, and you don't even need to do the whole dynamics, just pick some points. Okay? There is more to this paper, but this is the summary. And okay, 5 minutes, so I'm going to just tell you now the issue of self-averaging. So what does it mean to have a quantity that is self-averaging? So it's self-averaging when the relative variance, so the variance divided by the square of the mean, when this relative variance decreases as we increase the system size. If this is true, it's great. As you increase the system size, you can reduce the number of samples, so very good if we are doing numerics, if you're doing an experiment. It means that the physical properties of the system does not depend on the realization that you picked. Great. If this is not satisfied, then you're in trouble. You have to keep doing big averages, even when the system is very large. So the issue of self-averaging for the spectral form factor was discussed already in Planck's paper and others back in the 90s. What we did with Maud in this work was to study this relative variance analytically again, using random matrices. And we showed that the quantity is not self-averaging at any time scales. We are not only concerned about the the correlation whole any time scale. No? So you see things go upside down. This is small size. Orange is small size. Purple is big. We increase the dimension, and the fluctuations get even worse. In the region of the hole, in the region of saturation, this is 1. So 1 is bad. It should be decreased. So this is all analytical. In the case of physical models, the behavior is similar. This is also 1. Analytical results for short and long times. If we increase this order, things get worse, bigger fluctuations. How about the spin autocorrelation function? Well, this is a local quantity. So this quantity is self-averaging. It's a local quantity. It is self-averaging at short times. So this inset can explain better what is seen here. No? So it is decreasing. But in the region where the whole, these dynamical manifestations of chaos appear, things get worse, even worse than in the survival probability. So all that then to ask, what are we going to do? And the answer was already in Adolfo's paper. Tomaz was also part of some of these works. The idea is open the system. So I'm showing one paper, but Adolfo has many others on this subject. And what we have here is the spectral form factor. No? So it's the spectral form factor or survival probability where these components of the initial state now are Boltzmann factors. And this kappa here is the decoherence coefficient. So dark blue is one realization kappa 0 and big fluctuations. You put the kappa there, so you open the system and follow this curve here, you see that it becomes smooth. This is one realization. That is great. So let's open the system, but careful, don't open it too much because then you lose everything, the fluctuations and the whole. See? So okay. It's like as if you had dephasing in your system. Yeah, well, you can play with other scenarios. No? This is the simple one that I'm showing to you. He has other kinds of, you see, this is another scenario that Adolfo studied as well. You could play with others. The purpose of this is just to say, if I open it in this scenario, we are reducing the fluctuations. Of course, there is more than you can do and analyze. I don't have all the answers. So these are the fluctuations, closed system. Red here, when we open, decreased a lot. Now these dotted lines is the relative variance, which is 1 when it's closed, and shoop, becomes tiny, tiny when you open it. Right? So the ramp is, okay, let me show, this is from Adolfo's paper, yeah? You see the ramp is here. In the open case, so these lighter blues, they are open cases, you see? They're all open. I didn't check. You've been working with open systems. Did you check? It's not, okay. Okay, I never checked, so you know. I was happy to see that there was still the hole. In this figure, it looks clean.
Maybe we can let the speaker
that's
finish.
That's something I should check, yeah? Okay, but so it became tiny, tiny. This is good. And then we did scaling analysis of this plateau, and then for different temperatures. And then we see them decreasing as we increase the dimension, so we are very happy. There is much more in this paper. Adolfo's group did a very nice thing, making this parallel between non-unitary dynamics and averages. So I'm really simplifying things a lot. What are we doing now? Still with Adolfo, and Edwin is really leading this. Studying our physical models, different quantities. When we open it, checking how these fluctuations behave during the whole evolution, checking the distributions of these fluctuations. And now, since Manas told me, we're also going to check if it's linear or not, that the ramp, okay? But different models here also banded random matrix. So I just want to advertise Edwin here. He's great, Fulbright fellow. He's graduating. He'll be looking for a postdoc. Keep an eye on him. He's really good. Okay, so that's the end of the story. We probably can detect the correlation hole experimentally. Amit may have more to tell you about this. if the correlation hole appears exponentially long times for thermalization, how can we handle self-averaging opening the system? So thank you.
Thanks, Lea, for the wonderful talk. There was already a lot of interactions, but we can take a couple of questions maybe.
Yes, could you go back, please, with the blue fluctuations a bit before that? That one. So what we showed, I think, is that the biggest spikes, those that are of the
biggest
spikes that go down, they are exponentially thin in time. So I'm a bit worried that when people do averages, how do they? It depends how you bin the time a lot, because suppose you bin a time and you have a bin and you have the biggest fluctuation during that interval. That may not be a good procedure because the spikes, like this, the biggest ones, although there are, they don't contribute to averages. This is what we proved. So there could be things that are closer to the line that do contribute to average, smaller fluctuations. But the biggest ones, the most spectacular ones, for sure do not.
But okay, so you're talking about when we do the averages in the isolated system, right?
Yeah.
But then we do 10 to 5 data points. And if there is one big spike there, it's not going to affect the averages, right?
Yes, but the spikes themselves scale to 0 in their width as you consider larger systems. So the biggest ones, no? So I'm not making a statement of all fluctuations, but the big spikes, unless we got it wrong, should not contribute to the non-self-averageness.
Okay, no, that's good.
Unless we got it wrong.
I don't
We have time for one more question.
There is not there.
Yeah, I was just from a non-expert in this area, could you give a index card explanation of why there is a correlation hole? Is it a kind of Gibbs phenomenon or?
Okay, the correlation hole shows up because we have correlated eigenvalues. That's the simple answer. Now, if you want to get a physical explanation, I think that's what you are after, right?
It just comes about from the level separation and inherent in
it's level repulsion. Yeah, so the levels are correlated, just like in random matrices. Then you get this correlation hole.
But wouldn't that give you a correlation bump, so to speak? Or?
It does. If you're studying an entropy, we have one paper that we called correlation hole and bulge. What was for the bump? Depends on the quantity that you are measuring. But for these other quantities, we saw the tiny bumps.
Okay.
But for the survival probability, it was a clear hole.
Okay, I thought Lev had another question, and that's the last one we're going to take for now.
Just a quick question about this averaging. So you have two types of averaging. One is over states initial, then you average over Hamiltonian realizations.
That is a good.
What was the crucial contribution there?
This is good. I think the most important is averages over realizations. Because if you pick just one realization and look at the average over initial states, that, I don't know, I saw bigger fluctuations there. Yeah, I can give you more details, but usually we do 3 averages: initial state, realizations, and running averages as well to make it really smooth. But I think the essential is realization.
Let's thank Lea again for the talk.